Ladies and gentlemen, welcome to this lecture on the sizing of the electric vehicle powertrain. In this lecture, we will learn how to estimate the forces on the vehicle and the power that needs to be delivered by the powertrain to control the vehicle speed. There are three learning objectives for this lecture. First, what are the forces acting on a vehicle when it is driving? Namely, the rolling resistance force, the aerodynamic drag force, and the gradient force. Secondly, how to use the traction forces to control the vehicle speed. And finally, how should the powertrain of the vehicle be sized? Let us first start by analyzing the rolling resistance force. The rolling resistance force occurs due to the friction between the tires and the driving surface. The rolling resistance force is zero at standstill of the vehicle. When the vehicle slowly starts moving, the rolling resistance force acts in the direction opposite to the direction of motion, and it can be calculated by the rolling resistance coefficient CR multiplied by the normal force between the vehicle and the road. For a flat surface, the normal force is the vehicle mass m times the gravity g, or in other words is the weight of the vehicle. In case of a road with an inclination angle theta, the normal force becomes the weight mg multiplied by the cosine of the road angle theta. It is important to note that the rolling resistance force is independent of the vehicle speed, and it always is opposite to the direction of the vehicle. The coefficient CR should be low so as to keep the frictional losses low. For modern cars, it is typically around 0.01 to 0.02. As the vehicle speed increases, the aerodynamic drag force opposes the vehicle motion, as the air is forced to move and flow around the vehicle. It can be calculated as a product of the aerodynamic drag coefficient CD, the frontal area of the vehicle AF, the air density ρ, and the square of the vehicle speed V, the entire expression divided by 2. It is then important to note that the aerodynamic drag is independent of the vehicle mass, but has a very strong dependence to the speed of the vehicle. That is why in a car, the aerodynamic drag force is higher than the rolling resistance force when the speed is about 70 to 80 kilometers per hour. Secondly, the coefficient of drag is typically about 0.25 to 0.35 for a modern car. SUVs with their typically boxy shapes have a much higher coefficient in the range of 0.35 to 0.45. The third force that acts on a vehicle is the gradient force, and it occurs when the vehicle is driving on an uphill or on a downhill road. The gradient force is due to the longitudinal component of the gravitational force, namely mg sin theta, where theta is the inclination angle of the road. As seen earlier, the cosine component mg cos theta contributes to the normal force and the corresponding rolling resistance force. The gradient force and the angle theta are negative when driving downhill, and the gradient force and the angle theta are positive when driving uphill. The road gradients are expressed as a percentage in terms of the tangential value of theta and have value typically between plus or minus 10%. If we now consider a vehicle moving on an inclined surface, then the aerodynamic drag force, the rolling resistance force, and the gradient force act on the vehicle. If we now include the traction force provided by the vehicle powertrain, then the net force on the vehicle F net is the difference between the traction force and the sum of the forces due to the aerodynamic drag, the rolling resistance force, and the road gradient. By Newton's second law, the net force on the vehicle is equal to the product of the vehicle mass and the vehicle acceleration. Therefore, we can control the vehicle acceleration and thereby the speed by controlling the traction force that the powertrain produces. The traction force is in the driving direction most of the time, but can be zero when the vehicle is coasting, or even negative when the powertrain is under regenerative braking. If we now expand the equation for the traction force, we can see the factors that influence the vehicle forces. The vehicle mass and the road angle affects the rolling resistance and the gradient force. The vehicle's speed determines the aerodynamic drag force, and the rest of the traction force decides the vehicle acceleration. If we need to estimate the power delivered by the powertrain P tract, then we need to multiply the traction force F tract that we saw earlier with the speed of the vehicle V. It is important to realize that in this lecture we only take into account the forces in the forward and reverse direction as they influence the powertrain. The forces in the other directions are neglected for simplicity. Secondly, the forces in the vehicle are assumed to be acting at one point. In reality, the forces are distributed all over the vehicle. Let us now look at a force-speed diagram of a vehicle with a mass of 1.5 ton, a frontal area of 2.5 meter square, and a speed range between 0 and 200 kilometers per hour. From the formula for the traction force, we can calculate the force at each speed level for 0 vehicle acceleration. Those points make a force speed curve of this car. When the speed is close to 0, then the traction force is used to overcome the rolling resistance force. As the speed increases, the traction force needed increases fast as the aerodynamic force increases with the square of the vehicle speed. Let us now investigate 3 road conditions: a flat road, a 5% uphill gradient, and a 5% gradient downhill. We can see in the downhill condition that the traction force needed for low speeds is negative, as the gradient force is larger than the combined rolling resistance and aerodynamic forces. On the other hand, the uphill gradient requires a significantly higher traction force for the same speed than the 0% or the downhill gradient. Finally, let us consider the case when the vehicle has a finite acceleration. This is the force speed curve for the same car with 0% gradient and 0 acceleration. Since the mass of the car is 1500 kg or 1.5 tons, for every 1 meter per second square acceleration, an extra 1500 newtons of traction force is required from the powertrain. Besides the traction force, the electric vehicle battery also provides the power for several vehicle auxiliaries. This can be the heating, the air conditioning, the lighting, the car wiper, etc. Hence, the net power delivered by the traction battery P-bat is the sum of the traction power P-tract that we saw earlier and the auxiliary power P-aux. At times, it can be that the auxiliary power for heating, ventilation or air conditioning is quite significant when compared to the power required for driving. To conclude, the forces acting on a vehicle when it is driving consist of the rolling resistance force, the aerodynamic drag force and the gradient force. The drivetrain provides the traction force which can be controlled to change the vehicle acceleration and hence the vehicle speed. Thank you.